This is a DC circuit with one bulb. Turn it on, and the current flows. This is a DC circuit with two bulbs. Turn it on, and the current flows more slowly. What do you think will happen when you add a third bulb? Check it out. Add a third bulb, and the current will flow the slowest of all. If you're in any doubt, put in an ammeter and see. .3 amps. If we take out the third light bulb, .45 amps, and if we even take out the second light bulb, .9 amps. That is because every one of these bulbs has a certain resistance. The more resistance you have, the less current will flow. That's definitional. Resistance is how hard it is for the current to flow. In a series circuit, you are adding checkpoints. If you have more resistors, you have more traffic lights, you have more checkpoints, you have more things holding you up. Add more and more and more resistors. You're going to get higher resistance, and the current is going to go down. Here's our circuit. One resistor as before. This time it's just a resistor, not a resistor that glows, aka a light bulb, and there's our 0.9 amps. But this time we're going to make it into a parallel circuit. This time, instead of adding traffic lights, instead of adding checkpoints, we're going to add options. We're going to make a parallel path. And then we're going to make another. See what happens when we add more options. What do you expect will happen when we add another option? If you've done your lab correctly, the current should go up again. Why? Why is it that for a series circuit, when you add more resistors, the total resistance goes up and the current goes down? But for a parallel circuit, when you add more resistors, the total resistance goes down and the current goes up. It's the complete opposite. The analogy I like to use is the traffic model, where each resistor or light bulb or appliance with resistance is a traffic light. Think of how many traffic lights you have on your commute to school in the good days, not the COVID-19 days where traffic is a thing. If you have to pass through the traffic light at Lake and Waukegan, at Lake Cook and Waukegan, at Lake Cook and Finkston, you're going to be getting your crime and punishment reading for English class done over audiobook while you sit there in traffic. And if you have to add yet another traffic light to your morning commute, that is going to make it harder for you to get to school. And that is going to make the current, that is to say your travel time, lower still. More traffic lights. It's a bad thing. But what if you had a choice of different parallel routes to go to school? You could, of course, take the highway, but everybody else is taking the highway in the morning, so there's going to be a lot of traffic. If you don't want to take the highway, what could you take? Well, you could take Waukegan. Guess what? Everybody else who's not taking the highway is also taking Waukegan. If you're coming from the east, you could take Sheridan. Oh, and in addition to Sheridan, there is that little known way through the woods It's called Forest Way. It's right past the Botanic Garden. Nobody's ever heard of it. But that means there's practically no traffic on it. It's practically empty. Sure, the speed limit is like 30 miles an hour, but you're actually going that 30 miles an hour the whole time, except for the stop sign at Tower Road. You don't have to sit in traffic. Check it out. All the people who are on Waukegan are easing up the traffic on the highway. All the people who are on Sheridan are easing up traffic in both places. And taking Forest Way not only means you can move faster, it means that you, having taken another option, are easing up the traffic on all the other roads by not being there. It's many more than 10 years ago that just as we were teaching this material, we had a big, enormous fire drill right in the middle of physics class, and the whole school had to go outside to the basketball courts. It was May. Yay! The sky was blue. It was freezing cold, and we're all out there without our coats. So it's like, okay, who burned the bagel in the teacher's lounge? Finally, the all clear signal is given, and the whole school makes a massive rush for the cafeteria door, and of course discovered the hard way that the cafeteria door opens outward, and if 158 people are smushing poor Igor against the door, he's not going to do a very good job of opening it, is it? So we're all pushing and shoving at the back of the crowd as Igor finally finds his keys, opens up the door, and everybody's pushing and shoving to get inside. And Adam Rudolph and Kevin Rahmani, and I think Adam's brother, and Eitan too, start jumping up and down in the back of the crowd. And they're like, Miss Eliezer, parallel circuit! And the four of them start running as fast as they can possibly go around the building to the main entrance, which has to be open because that's where the firefighters get in. And I knew what they were talking about, pushing and shoving at the back of the crowd. Yeah, we're all like right there at the back door. But there's 150 people's worth of traffic at the back door, and they were betting me that if they took the long route with the longer path, yes, it's longer, but it had lower resistance because there was less of a crowd, that they could run all the way around the perimeter of the school and get in and be inside in the warm faster than those of us who were pushing and shoving on the main route. And you know what? They were perfectly right. We got in to the door of the Shapiro Dining Hall, and there we were. And there were the 4 CP physics guys in the hallway jumping up and down and giving each other high fives because they were warm and dry and physics had gotten them in there faster. In a parallel circuit, if you can take another route, you will free up the traffic for everybody. You'll get there faster, and so will everybody else. Don't think of it as adding more resistors. Think of it as adding more paths or more options. So, if you're looking in a series circuit and you've got a bunch of resistors all in line, you've got 20 ohms and 30 ohms and 40 ohms should be giving you a grand total of 90 ohms of resistance. And if you use Ohm's law, total current should be total voltage divided by total resistance. Well, that's fine. We've got the total voltage. We've got the total resistance, 120 volts, write down the unit to make sure you got the correct number, over 90 ohms, write down the unit to make sure you got the correct number. You should be getting 1.3-ish amperes, don't forget your unit, of current. Now, if you Google a formula for parallel circuit resistance, you'll notice that you don't so much get a formula as a video explaining what to do. Junctions are complicated. If you just click on something and say, here is the formula, you will note, and this is what you're going to see in tomorrow night's lecture and practice deriving, that the total resistance is a denominator, and that's how it works. If you add more terms to the denominator, if you add more resistors to the denominator, then the total resistance gets smaller because you've got a nice big denominator, and that means the current can get larger. Notice that what you have here is a formula full of fractions, and it is very, very, very easy to forget to type a fraction in your calculator. So the official formula you're going to be writing down is 1 over giant fraction, 1 over R1, plus 1 over R2 plus 1 over R3. But the easy type version will get you the answer a lot faster. If you have 4 100 ohm resistors wired in parallel, do this on your calculator in fractions. Do 1 over 100, or if you have a -1 key, use the -1 key. I like the -1 key. I find it faster. And there's the 4th. And don't forget your very last term of all. If you hit this, if you get an answer of 0.00 something ohms, proofread your formula. You forgot that all of this was in the denominator. The easy type formula for parallel resistance, the one that gets you an answer in a hurry, is parentheses R1 to the -1 plus R2 to the -1 plus R3 to the -1 plus R4 to the -1 whole quantity to the -1 power. 4 resistors in parallel should be giving you a total resistance of 25 ohms if you're reading the formula correctly. You'll see in the next lecture, proofreading, the total resistance in a parallel circuit should always be a little bit smaller than the smallest resistor. What's a little bit smaller? Well, in this case, the smallest resistor was 100. Who are we kidding? The only resistor was 100. And the total resistance is 25. It was not 0.00 something. Now, if you connect this circuit to a 1.5 volt battery, then you have 1.5 volts of resistance, don't forget your volts, divided by 25 ohms of resistance. That's the resistance, so it's 1.5 volts of voltage divided by 25 ohms of resistance should give you 0.06 amperes, or if you're talking like an electrician, 60 milliamps. And you know from the notes you took on current that 60 milliamps is well past the dangerous threshold of 15 milliamps and just under the deadly threshold of 70 milliamps. So it's worthwhile to really take your time and do this right, because you don't want to turn up as Kentucky Fried Chicken. Here's the analogy I was talking about before. A series circuit has you going through huge long lines, checkpoint after checkpoint after checkpoint. The more checkpoints you go through before you finally get to your seat, the harder it's going to be to get there, the slower you'll move, and the longer it'll take to get you there. You'll have a fairly low current. If you add more resistors to a series circuit, the total resistance goes up and makes the total current go down. But a parallel circuit, those aren't checkpoints, they're gates. I mean, yes, a gate is a checkpoint too, but you have a lot of gates in parallel. You have many parallel checkpoints. In a parallel circuit, each gate is its own private line. You have potential, that is money in your wallet to buy the tickets. You buy the tickets, you go through the gate, you deliver the tickets, and then you can go straight to your seats. You've got many parallel paths. In a parallel circuit, the current only goes through one of the many resistors to choose from. It can choose, just like you can choose not to stand in the line at gate 41 because there's a large and annoying family in front of you, and not to stand at gate 40 because there's a big long line. You can choose to go to gate 42. I think most people in the class are going to choose gate 42, except for those sarcastic naysayers who say, oh, everybody else in the class is in gate 42. That's going to be a pretty long line. I'm going to go to gate 40. And you know what? That's what the electrons do too. A few of them go here, a few more go here, and most of them go here because the current tends to the path of least resistance, and in gate 42 we've got the path of least resistance. If you add more resistors to a parallel circuit, the total resistance goes down because there are more paths or there are more different options. This makes the current go up because there are more places it can flow, and that frees up the current to go faster. And here are the formulas I was talking about before that you're going to be deriving in the next lecture. Now, review questions. What's the problem with the blown fuse? Trick question, not the fuse. The problem with a blown fuse is that the current was too high. That was the problem. You're going to be overheating something. You're going to be running the risk of melting plastic insulation and solder. You're going to get smoke. You're going to get fumes, and you're running the risk of electrical fires. How do you fix the problem? Step 1, turn it off. Step 2, lower the current. How do we lower the current? By increasing the resistance. Now we can be more specific than we could last week. Now we have great ways to increase the resistance. I mean, you could, of course, take a chainsaw to your appliance and put in more resistance bodily. More likely, you've got a circuit, not just one appliance. You've got a lot of things plugged in. If it's a series circuit, you should add more resistors to the circuit. You don't have to take a chainsaw to anything to increase the resistance and lower the current. You'll see in the next couple days why you don't really get series circuits anywhere but in first year college prep physics class. 4 reasons that will become pretty obvious pretty quickly. Almost everything in your world is going to be wired in parallel. If you haven't written this down, write it now. How do you lower the current in a parallel circuit? How do you decrease the current? That means increase the resistance in a parallel circuit. Pause this video if you haven't written it down yet. Think about it. Write it down. Ready? No, seriously, pause this video and actually think for yourself. You got it written down? You sure? Okay. In a parallel circuit, you should be taking out resistors. You should be unplugging things and switching things off so that you have more resistance and less current. There's our series and parallel. And which one sounds a little bit more like what we do in real life?